Hi, I'm Simon. I'm going to tell you how to write well-behaved value wrappers. Before I go on to define those terms, at Microsoft we have this survey, which it would be great if you can fill in, and you can win an Xbox One. Yay. Yes, thank you. Okay, with that out of the way, value wrappers. What do I mean? What I mean is types with value semantics which can store objects of any type. So some examples of this are stood pair, optional, variant, all from the standard library. Some of you may be familiar with Jonathan Beccara's name type library, which he uses for his strong type posts. And by value semantics, I mean if you copy the wrapper, you copy the value. If you move the wrapper, you move the value. It acts kind of like this was just an int or something like that. Well-behaved, I have two criteria I'm particularly interested in. The first is one which hopefully we're all interested in as C++ programmers. We want our code to be fast. And value wrappers can have some overhead if you do not write them correctly. So I care about performance. I want everything in this talk will either focus on performance or on being unsurprising. Now, we all care about being performant, but it seems like a lot of us in C++ do not care about being unsurprising. Well, I do. So I want to make these wrappers unsurprising. We don't want all of these crazy edge cases which we hit so often in the C++ world. A cautionary tale. I found this comment in the source code for a huge project, one which I'm actually using to present these slides. It says, note, GCC has missed optimizations with maybe, the type it's talking about, in the past. And it may generate extra branches, loads, and stores. Use with caution on hot paths. It is not known whether or not this is still a problem. If the people who wrote this comment are watching this talk, either in this room or later, then hopefully you can apply some of these things I'm going to be talking about so you can get rid of this comment and actually fix the problem. Comparison operators, starting off with something we're presumably all familiar with. This is about the simplest wrapper type I could think of. You know, it takes a template parameter, stores it inside. We might want to write this code. We have a wrapper of ints, and we like to be able to compare ints. So maybe we want to be able to compare our wrappers as well. In some cases we don't, but in a lot of cases we do. And this will not compile unless we do some extra work. So we could go ahead and do that work. After noting that this is absolutely not surprising behavior for many cases, we want this to compile. So if we start with this, blank slate, go ahead, write all our comparison operators. Might look something like this. These are all the comparison operators for my implementation of stood optional. And this is pretty much exactly what you have to write if you want to implement this. There's no getting out of doing this work. You can implement some in terms of others, sure, but eventually you have to write all these overloads, and it's not going to be pretty. So now if we write all that, it compiles. So we are unsurprising, but it's so much code. Like, we do this so often, and it just makes me so sad. Has anyone seen this film? Lego Movie. Yeah, great film. My favorite character in the Lego Movie is this guy. Loves his spaceships. He particularly likes this one. But in C++, instead of looking like this, our spaceship looks like this. So this is the new spaceship operator from C++ 20, and it's going to solve some of our problems. So it goes something like this. We have two objects, A and B, which we want to compare. So we do the spaceship operator on them and compare the result against 0. That's going to tell us if it's greater, less than, or equal to the other one. You don't tend to actually write the spaceship operator, but this is kind of how it's defined. So if we have a pair, this is not exactly std pair, this is just like a simple pair value wrapper type. We can actually get the compiler to do essentially all our work for us. If we write equals default, then the compiler will generate comparison operators which lexicographically compare by member. So we will first compare by t, and then compare by u. And it essentially does what you want, Jason. Is it automatically const-expr? I can't remember off the top of my head. I would hope that it would be. And maybe you have to write that on the declaration. I'm not sure. I can check afterwards and get back to you. So this generates code kind of like this. You don't have to worry so much about those decal types and common comparison categories. But of course, this being C++, it doesn't just return an int. It returns something a lot more complicated, which would be an entire talk on its own. But you can see it's generating code to compare t and then compare u. So now we've gone from all this code, and with the power of spaceships, we've gone to this. This is code I stole from Barry Revson's blog post. But this is so much easier, yes, Jason? Right, I did do have const-expr there. You're right, so that's probably needed for it to be const-expr. So now we've gone from being unsurprising with a ton of code to just being plain unsurprising. This is a huge win. So that's enough for comparison operators. I'll move on to noexcept propagation. So noexcept is used quite a lot by some people, not so much by others. If you have one piece of advice you want to follow, it's make sure that you propagate whether your move operations and your swap operations are noexcept, because this matters. For swap, people will write code which assumes this thing can never throw. If people use the copy and swap idiom, for example, they will do this thing, and if it throws, you're going to break someone's code. Don't do that. For move, it has even more worth, because say we have this vector of optional, and this tracer type is just something which keeps track of copies and moves. If we propagate noexcept correctly, then we get 100,000 copies and more than 200,000 moves. But if we don't do this work, then a bunch of those moves turn into copies, because std vector internally will not move the underlying objects if it could throw, because then it could move something, it throws, the data's lost. We hate data loss, so vector doesn't do that. And you do this by, say we have a move constructor for optional here. You don't have to worry much about the implementation. But we can do something like this. Add noexcept, and check if the underlying type is no-throw move constructible. If it is, then this is noexcept. If it's not, it's not. So this does our work for us. You may be familiar with this quote. Too explicit or not too explicit? That is the question. And that indeed is the question. Say again, we have our wrapper type. This would be a compiler error. We have a wrapper of ints. We try and initialize it with an int. Seems reasonable. But it doesn't compile. So maybe we say, OK, this is fine. I'll write a constructor which takes a t. And this is fine. Obviously, some of you are super smart, and you'll be, yeah, we use perfect forwarding. Feel very, very happy with ourselves, very pleased. But then, someone comes along and writes this very aptly named type. Oh no. This has an explicit constructor from bool. So then if someone writes a function which takes a wrapper of oh no, then we can pass true and it will implicitly convert, even though the author of this type presumably put explicit there for a reason. Oh no. So this is surprising. We don't want this. So what we usually do at the moment is we write two overloads, and we use svne, like std enable if, to select between them. So don't worry if you don't understand enable if. It essentially means that this version will only be a candidate if those things evaluate to true. So we have one version which is not explicit, and we have one version which is explicit. And the only thing we switch is this is convertible. So if the underlying type converts implicitly, then we convert implicitly. Otherwise, we don't. And now this compiles, and it's great. And this doesn't compile, just as we hoped. So we're unsurprising, but we have code duplication. So this isn't great. We have noexcept bool. We mentioned it literally in the last section. What if we could have explicit bool? This would solve our problem. Instead of having two overloads, one which is explicit, one which isn't, we just move this is convertible thing down into this explicit specifier. And this does the same thing, but it's just one overload. The code is clearer, for some definition of clear. But now we've gone from unsurprising with code duplication to just being unsurprising. Success. And this explicit operator is actually in C++20. So if you happen to use C++20, then, oh, great. But also you can use this.
Also give me your time machine.
Yes. If you have a time machine, Gashper said, you can use it, and that's true. OK, conditionally deleting special members. Now we're getting into some arcane stuff. So if we have a simple implementation of optional here, it's essentially just a union of a t and some like dummy type that we don't care about, and then we have a Boolean to say whether we're engaged or not. So if we have a copy constructor like this, it's just a kind of normal copy constructor. And we have a normal destructor which checks if it's engaged and then destructs. Then we have to be very careful because optional is not a type where you can just default your operators, because it might have to delete, it might not. It might have to copy, it might not. So in cases where you do have to write your own copy constructors and your own destructors, you need to think about whether you have to conditionally delete your special members. So this is like not a very good reason, but part of a reason is you get better error message. In the first case where we don't delete, then we kind of get something which is internal to the implementation rather than just saying what went wrong. We had a deleted copy constructor of optional. More important is if we want to check if something's copy constructible, say we want to svne on this, say we want to do a context for if, we will get the wrong answer if we don't propagate our deletion, because it's not svne friendly, essentially. So if we do not do this, we get the wrong answer, and this can lead to surprising errors. Your code will hard compiler error, even if you think that it shouldn't. So this is surprising again. So again, back to our simple optional implementation. What you actually kind of need to do at the moment is you make a base class. You shove all of your details, all of your members into this base class, and then you privately inherit from this class. And you privately inherit from something which will delete your constructors and your assignment operators. And you kind of have to do this with inheritance just because of how deletion of special member functions works. And so these delete CTOR base and assign bases, they look something like this. We have like a class which will check if it's copy constructible and move constructible. And then we have a specialization. So if these are both true, then they're both defaulted. If it's true and false, then it's default delete, delete default, delete delete. Make sense? It's just dealing with all the different cases, and we do have to write all that code each time, even though it's essentially the same. And then we do the same for delete assign base. And so this will now do the right thing if we try and check if it's copy constructible. So we're going to being unsurprising, but a ton of code. Again, maybe seeing a pattern developing here. So concepts would help a lot with this, because we can actually constrain non-templates like this. We can say we require it's copy constructible and require our move constructor, the underlying type is move constructible, and then do all our work in there. And this is great, because we've gone from being unsurprising with a ton of code to being unsurprising again. Triviality propagation. Who's even familiar with the idea of trivial copy constructibility? Maybe about a quarter, third of the room or something. Okay, so this is getting a bit weird. This is the system 5, system V, I can never remember. The Holy Tome. A quote, an object with either a non-trivial copy constructor or a non-trivial destructor cannot be passed by value because some objects must have well-defined addresses. Now this isn't meaning like quite C++ passed by value, but it does mean like putting it on the stack versus passing it in registers. Passing in registers is passing by value in this case, because you're just copying it into a register. So this is important. So trivial copy constructor is defined as this. The copy constructor has to be defaulted or implicitly defined. There's some extra wording in there, but I kind of want to keep it simple. Can't have any virtual member functions or base classes, and all of the base and member copy constructors have to be trivial. Kind of like you might expect. And it's very much the same for the, yeah, sorry, question.
I'm sorry, is that no virtual base classes or no base classes?
No virtual base classes. Yes, so the question was, is it no base classes at all or no virtual base classes? Just virtual base classes. And the trivial destructor is essentially very much similar. So we could actually have a static assert which says if it checks if my optional int is trivially copy constructible, then currently this would compiler error, which means, because what the ABI says, we cannot pass an optional int in a register because this check fails. Similarly for is trivially destructible, same thing. And this is not performant. Pardon? Michael says it's not a word, and sure. It is for the purposes of this talk. I define what is purpose. Okay, so this is some assembly code produced courtesy of Matt Godbolt. And so you can see if I do not propagate, then I essentially pass things on the stack. And if I do propagate the triviality, then the compiler just works out what value I add, in this case 42, because of course. And it just moves it into a register and just works. Gets even worse if I start to pass this as a function argument. You see this is starting to be more code using the stack more. And then if I don't propagate trivially destructibility, then it gets even worse. And then even worse if I use vectors. I mean, this is not so bad. It's essentially an unrolled loop, destructing all the underlying objects. But you can see how this kind of thing, when I'm just trying to use ints, it's not great. We want this stuff to be fast. So say we have our destructor here. Well, a lot of people say, oh, it's fine, we just use SVNA. It'll work. No, it does not work. You cannot have destructors or copy constructors or move constructors which are templates, so you can't SVNA them away. Them's the rules, I don't make them. What you can do is make base classes again. Private base classes are used all over the place. If you ever look at a standard library implementation, you will see these. And so we do our actual destruction in our base class. And this version is for when our thing is not trivially destructible, so we have to call the destructor. And then we have another case where we make a template specialization for when we do not have to call, and we just default it. And then we do the same with the copy constructor, and with the copy assignment, and the move constructor, and the move assignment. C++ is great. Yeah, and then we inherit from, these all inherit from each other, and then we inherit from the top level one, and it's all fine. We just default our destructor, and the base classes will work out what to do, essentially. So now this compiles. And this compiles. So we're performant. Can anyone tell me what comes next? But with lots of code. There we go. Starting to catch on. OK. So how do we fix this? Well, we can actually use concepts. Again, we do need this other paper written by Barry Revson and Andrew Sutton, I believe. It's not been discussed yet. I think it's going to be discussed at San Diego, but it essentially means that it would make this work. Currently, just because of some wording, it's not quite there. Hopefully, we'll get this, and it will all be great. And we can go from being performant with a ton of code to just being performant again. For 5 more seconds, this one. So you can have a look. Oops. Ah, there you go. Yeah, so you just say we require copy constructible and move constructible. And I can't remember exactly the wording in the paper, but it means that if these things are removed, then you retain triviality. Yes, Michal?
So is the status quo that they are not trivial?
So the question was, is the problem... Yeah, so the question is about the current wording. I can't remember exactly. I think the current wording means that even if they're removed, it's not trivial. And this paper makes it such that they are trivial.
And that works for destructors as well?
Yes, that works for destructors as well, Gershwin. Thank you. OK, I noticed JF is in the room. So I stole his tweet. How do you know if a C++ developer is qualified? JF? You check their CV. I did not plan for JF to be in the room, but this is so much better. Another answer would be, you look at their references. Yeah. And this is what I'm going to talk about now. Ref-qualified accessor functions. OK, so this is what a lot of code I see looks like. You know, you have you want to write an accessor function. It looks kind of like a deref. This would be what you might write for optional or something like that. This could just equally be called get or value or whatever. People have different names for this. But you'll see this a lot. People will have a non-const version and a const version because you want it to work in both cases, right? This. Can anyone tell me whether these lines copy or move with this operator? Copy. First one copies, second one moves. Because in the first example, we move and then we use our operator, but our operator doesn't care about whether it's called on an L value or an R value. Whereas the second example, you do the dereference or whatever, and then you do the move. So this is always going to be an R value, so you'll do a move. This is not performant or unsurprising. So what we can do is instead of just having a non-const and a const version, in C++ 11 onwards, we can add reference qualifiers. Yay! Multiply the amount of code we have to write by 2. Constrefref. I have a slide on constrefref. Oh dear is the response. Yes, very much oh dear. Constrefref. Here's one reason why constrefref might actually help. So if you use something like let the audience compose themselves. So if you have something like stdcref, which creates a const reference wrapper, this actually has the const ref version deleted so that you do not actually accidentally make references to temporaries, because it will just be deleted, be destroyed, and it will be undefined behavior. So yeah, so without const ref, you get whatever your favorite undefined behavior metaphor is. And if you do the const ref version, then you get a proper compiler error. So I mean, it's an edgy case, but you know, it could be worthwhile. Gasper.
Whenever you have anything with universal references, const ref is perfectly valid.
Right. So the comment was, if you have universal references, sometimes it will just get deduced like that, especially if you're in a generic context and you have a bunch of things which are calling each other and returning from each other. These things turn up. So it's not like you're just going to be std moving a const thing because that's weird, but this does turn up when you have universal references in generic code. Thank you. Yep, so we have this, and we're now performant and unsurprising. But code duplication. Yes, quantification. But we could have deducing this. So this is a paper which myself and Gasper and Ben and Ben Dean and Barry Revson are working on. So the idea is that you deduce the type of the implicit object parameter. So this might look a little bit weird at first. If you're used to Python, where self is an explicit parameter to member function, then this maybe looks a little bit more reasonable to you. So we kind of qualify that this parameter is the implicit object parameter, and then just use universal references to deduce what the type is. And I have a feeling Gasper is going to tell me this code is slightly wrong, but I don't care. Yeah. Yeah, so we could do this. Does anyone have any questions about, so Jason, yes?
Well, Gasper said it wasn't wrong, but doesn't that require decal-type auto to actually get the correct return type?
Does it require decal-type auto? Sure, if you want to return a reference, then...
Isn't that the whole point? Is that you're returning a reference?
Yeah, you're right. This should have been decal-type auto, not auto. Thank you, Jason. Okay, so now we've gone from being performant and unsurprising, but with code duplication, and we've got rid of all of that. Okay, I wasn't sure whether to include this or not. SVNA, unfriendly callables. This stuff is hairy. I included this purely for the people who in the room maybe just knew everything I talked about, and you might still learn something from this one, so there we go. Right, we have our wrapper. Return of the wrapper. So then we have these member functions called pass-to. Now these take template, these are going to take like lambdas or function objects or whatever you want. It's just a template parameter. Don't worry about it being by value. And we have const, and we have non-const overloads. And this is important. And then we just have a decal type, because we want to, if this call is not valid, we want to sfine out. This is useful in many contexts. So we have this code. Familiarize yourself with it. It will be important. Non-const, const overload, sfine friendliness, using the decal type, calling the function. Okay, everyone got that? Okay. So now we have a wrapper of a foo, which just has a non-const member function. And we pass in a generic lambda, which will call do thing on X. Now this seems like reasonable-ish code. Again, for some definition of reasonable. Having to make these lambdas is super annoying in C++, but we have what we have. So we have a wrapper of foo. Foo has a member function, a non-const member function, important. And we pass a generic lambda, which calls this function. Okay, still with me? Yeah. Compiler error. Don't try and read this. I will explain what it says. It says passing const foo as this argument discards qualifiers. Where did const foo come from? The const overload, exactly. So there's no const in this code at all that we can see. We don't have a const wrapper of foo. If we did, this would make sense. More sense. It's not a wrapper of const foos. We don't see const on this slide, but there is const here. So what happens is these are both candidates for overloads which could be called. Right? They're both called pass2. The arguments look okay. So what we do is we check the decal type. We want the decal type because we want to be sfine friendly. And so we check the decal type of the first one, and it says, okay, we return, I think it's void. Yep, we return void. The second one, we try and work out what we return, and we hit compiler error because this call to x.do thing, where x is const qualified, is not valid because our member function is const unqualified. See what I meant about Harry? So just to explain in slightly different words, the fact that we have a const and non-const overload and they're both candidates means that these decal types have to be checked. And if the decal type does something invalid, which is not in an sfine context, then you're going to get a hard error. And there's fundamentally no way to get around this in C++ today. Both having the sfine friendliness and having const and non-const overloads. No way to get around it. This is surprising. This bug took me days to work out why my optional implementation was having some bugs. It's horrible. So what we could do is just get rid of the decal types. And this works because of how auto works. Essentially, auto is not worked out when you try and instantiate the signature of this function. It's only when the body is instantiated. That should have had return FTs in there, but yeah, so we could remove the decal type. It will compile now, but we lose the sfine friendliness. So now we don't get compiler error. Yeah, if you just look at this and think, oh, I removed the decal type, and suddenly it fixed everything, like what on earth is going on with this language? And that is a very valid question.
That also means you can't forward noexcept here, right?
You can't forward noexcept here. Yes, you couldn't forward noexcept either because it would have the same problem of trying to do something espionage unfriendly because it has to instantiate the signature of the function. So now we're unsurprising, but we're no longer espionage friendly. And this can be a problem. Some code relies on your stuff being espionage friendly. So we would like this, and it's literally impossible right now. But we can use deducing this again. Turns out we accidentally solved this problem without really realizing. We made this paper, and then Augustin Beres, I don't know if I pronounced his name right, he said, oh yeah, this solves my problem. I wrote a paper on this, and this actually fixes the decal type issue. So the reason is because this is a template, and it's going to deduce whether it's const or non-const, we're not having to instantiate invalid decal type types when we're doing our overload resolution. It will just say, okay, well, it's const qualified or it's not const qualified, so that's the only candidate. The other one's not even checked. And that's kind of how this gets around it. It's also, this is only a problem with member functions. If you have non-members, then we don't have this problem. And now we've gone from unsurprising, but no longer espionage friendly, to just unsurprising. So these are all the things which I talked about. I hope that you've come away with some ideas of how, in your own libraries, or maybe even problems you've seen in libraries you use, such as I mentioned at the start, how you could solve some of these problems. There are more kind of topics and things like that I could cover in here, but these ones are important for being unsurprising and for being performant. And that is how to write well-behaved value wrappers. Thank you. I have some resources here if you would like to check them out, and I will now take questions. Lots of phones, no hands. Hand, yes.
Just a quick question. Can you comment based on like what's available right now, for example, Boost with the optional variant and whatnot, how much of this is implemented by the implementations of value wrappers in the common C++-related libraries, and how much of this needs additional things to be done or needs work on the part of those authors?
Great, yes. So the question was whether I can comment for the kind of libraries which are used by a lot of developers like Boost, how many of these kinds of topics are actually applied and which ones could be applied to make it better. So for Boost optional and things like that, as far as I remember, they do all of this stuff. Same for all the standard implementations of optional now. Libstd C++ didn't propagate triviality for a while, which meant you got some bad code gen in cases, but they fixed it. So the standard versions, the Boost versions are all good. In fact, a lot of these ideas I got from like reading Boost code or standard library code, things like that. Things like that comment which was at the top. If you look at libraries which are used by, like written for major projects, but which don't aim to be kind of high-performance generic libraries in their own right, like LLVM, like Mozilla's kind of standard library type thing, those don't tend to follow these guidelines. So no LLVM's optional does not do a lot of this stuff, and Mozilla's maybe doesn't do a lot of this stuff. I'm sure there are many, many other cases which are the same. Unless it's a quick follow-up, I'll take Michal. Okay, Michal.
Yeah, so just coming back to what Casper said about propagating noexcept, that's have the same problem actually, because noexcept is only evaluated once you start instantiating the function. Is that still the case now that it's part of the type signature? It's part of the type signature, but it's not. But noexcept is not a spinning context. doesn't actually participate in overload resolution, right? So you don't actually start resolving the expression until you've chosen the overload. So the problem is only with spin 8 and not with.
Okay, Mikhail's comment was that I was incorrect about the noexcept having the same issue as the decal type, which was Gasper's question. And the reason is that noexcept, similarly to when I mentioned auto and how it's only evaluated once the function body is instantiated, it's the same for noexcept. It doesn't happen when you're instantiating the signature and doing overload resolution. Is that correct, Mikhail?
Yep.
Thank you. Gasper?
Please line up the microphone. Do you have I guess that means you don't have to repeat the question. So you had, the first time that you said that concepts solve this problem, there was some slide, I didn't understand how.
Whee!
Because the second time you had an additional paper cited, but the
Yes.
first time you didn't.
Yes, so the difference between, so this is the concepts plus P0848, and, geez, I have a lot of slides. Must be soon. Oh, yes, this one.
Yes.
Yes, so the difference is the current wording will, deletion works if the, if one of these is SPNA, well, not SPNA'd out, but the equivalent, like if the requires clause resolves to false, then this thing will be deleted. That's in the current wording. It's just it won't be trivial. And that's the thing which is missing. So the deletion works today. The triviality requires the other paper.
It can't be both trivial and deleted, though.
No, but
They have different conditions.
Okay.
yes. Yes, it can be trivial and deleted. Yeah, it matters in different cases whether the underlying type you're wrapping has them deleted, trivial, or non-trivial. There are 3 cases.
Okay, so optional is complicated for many reasons, but on one of your first slides, you had like pair.
Yes.
And I find myself often lately thinking when I'm working on something that's a simple wraparound int, like you had earlier also, of saying, well, you know what, all of this would be much simpler if all of the members are public, as it is here, and I have no constructors. Then
Yes.
I don't have to worry about any of these questions.
Right. So
I just wanted your comments on that. Thought.
yes. So I mentioned that briefly in the talk. Maybe I didn't. Yeah, maybe I wasn't clear enough. So some of these things only matter when you have to write your own constructors and destructors, like
So
for optional.
If you personally are writing a class like that today, you just leave it like that.
Right.
Okay.
Depending on what kind of things you want, because the comparison operators and the explicitness still matter. Because if you want implicit conversions, you have to do more stuff. And if you want the comparison operators, you have to do more stuff. But you don't have to do all the nonsense with like propagating, deletion, and triviality. That just works. It's only if you have to write your own.
Today you can mix them into this.
Today we can mix them in, you mean as like a private base class or something?
You would inherit from that and then mix in all the operators you want.
Right, yeah, so we could inherit from that and then mix in all the operators you want, which is kind of, it's a similar technique to how I deleted all the members by moving this into a base class, inheriting from that, and then inheriting things which deleted it. You could inherit from things which define operators. Yes, thanks, Peter. Mikhail.
All right, I have a question that's not directly related to the topic of this talk, but to something that appeared on the slides. Can you go to the assembly slides?
The assembly slides, I will have a shot. Anyone have any jokes while I'm...
I'm just trying to understand why the code then does a thing that it does.
Yeah, which one are you particularly interested in?
Whichever,
Okay, here we go.
but not the last one.
Okay, this is the simplest case.
Yeah, why the move absolute of the full operand?
Because this is an optional int, so it has the the int part and the bool. So this just happens to be the byte representation for encoding 42 and true.
Oh, because there is a high bit in that represents the bool of. Okay.
Right. Yeah.
Yeah. Thank you.
Just a sort of follow-up question. It seems like, I don't want to make you fast forward through the slide to the last thing, but you had a list of like, maybe 6 or 7 different requirements for what would constitute a good value semantic wrapper class.
That's right at the end, so I can find that one.
Yeah,
This.
right. It seems like this would be a great example case for a concept in C++ 20, like be able to say, this is a correct semantic value wrapper class type. Is that something you've thought of or plan to add as a concept for C++ 20 to be able to check all of these at compile time as you've laid out here?
Yes, that's an interesting question. I think because these are all related to instantiations of types. You care how it works for like optional int versus optional std vector or something like that. And checking behavior between instantiations is not really something which concepts map to well. Did you have a comment, Kashmir?
This is basically about encoding elements of programming.
Sorry, could you use the microphone, please? So I don't have to repeat.
This list is effectively about encoding all of the subfamilies of the elements of programming regular requirement. So, because that's what we think of when you say wrapper type, you're basically saying, we're going to forward all of the sub-things of regular that you can put into the interface, including comparison, because that's what the POE regular has, unlike our regular that's in the standard. Unfortunately, regular does not really encode all of these noexceptnesses and all of the spinanenesses and all of the various Boolean things like explicitness, for instance. That stuff is not in regular. So you have a family of concepts that is literally 2 to the power of things that you have over there. This is how many concepts there are here. So you could write probably something like 60 different concepts based on this. Like whether you have noexcept swap or not. Those are 2 separate concepts. Right. Or families, really, because every one of those can have an explicit constructor or not.
Yeah. If you special case each of the combinations of different attributes.
Yes, and that's what I'm talking about. Like, this is not one concept. This is a family of concepts. So what Simon is really talking about is like a giant decision tree that we're trying to encode into exactly. This is the concept you want, but it's like regular parameterized by all of these Boolean things. So,
yeah, it's like if you tried to plot this on a graph. This is not like a line of do I fulfill this thing or do I not. It's like a line for every single one of these, and you exist somewhere on this like nth dimensionaler plot.
I think my only point is this slide and the list of things seems sort of purpose-built exemplar for what concepts are supposed to provide conceptually. You're supposed to be able to tell the compiler, I want this to have ref-qualified member accessibles and trivial propagation and blah, 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 the characteristics that you want, and have the compiler be able to check that and tell me at compile time, you don't have this like you think you might.
yes, and we could write a concept that was parameterized by the bool for every one of these dimensions, and you could say, I want my type to fit regular true, true, false, true, true, false.
Yeah, it's the common was we could have essentially something which is parameterized by all of these and say, okay, I'm interested in these parts.
And you have like 4 or 5 common use cases.
So since you're next to the microphone, thanks.
4 or 5 common use cases that are typedeft as concepts for the common use cases, and then everybody could say, I think my type has these value semantics for this common use case, so I apply this requires concept, and boom, I get compile time checking for everything.
Yeah, you could do things like that. I think if I was to use something like concepts for things like this, it would actually be more for testing. So if I wrote out like a list of requirements that I wanted my generic type to have, and then I could have tests which run at compile time and check that I actually have like implemented triviality propagation correctly or noexcept propagation. I could have those checked in my test suites so that because a lot of this stuff is kind of subtle. So maybe if you don't know what you're doing and you make a small change, you might affect some of this. So you could have testing to actually check some of this stuff, and that might be useful. Any other questions or comments? Yes, Matthew.
How would you factorize that if you have a bunch of types to write, like you said, per, tuple, option? You need all those properties. Would you copy paste everything you've made so far for each of those types to have those properties?
Yeah, so the question is like, so if I'm implementing, like if I'm a standard library implementer or a boost implementer or something, and because I had examples at the start, like pair, tuple, variant, and all of those things, I would want to fulfill as many of these criteria which are applicable. So some of this stuff you can rip out. So for example, the deletion of the special member functions, you can have like one implementation of that which takes Boolean template parameters, and you would say, for example, for optional, you would just check if T is copy constructible or trivial copy constructible, movable, whatever. But for expected, you would check T and E, and you would just pass these in as template parameters, template arguments even. And then you could reuse all of that code, which I had like the 4 different things on the slide, that would all just work. And that is what standard libraries tend to do. They have like one version which takes bool parameters, and then they reuse it. So things like that you can reuse. Off the top of my head, some things like if you wrote your types in particular ways, you could use like mix-ins for the comparison operators, like Peter mentioned. For noexcept propagation, probably not. So yeah, it depends on the topic. Some of these yes, some of these no. Does that answer the question? Cool. There was another question over there I thought I saw. No. Good. Okay, thank you very much.